From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast asking the question, are we there yet? Exploring space is a lot like camping. You've got to bring everything with you, and that includes power. I did some reporting on a shortage of a vital resource to provide power in space when solar panels just won't do it. We'll talk to one NASA scientist who says that particular shortage is over, and the possibilities of exploration are limitless. But before that, I just want to take a minute and thank you for listening. We made it to iTunes New and Noteworthy, and also the top 10 in Science Podcasts. For that, I just want to say thank you. If you enjoy the program, be sure to let your friends know, and strangers too. Give us a rating and review on iTunes if you can. There's a lot more awesome stuff to talk about, so stay listening, and I'd love to hear feedback from you. You can follow me on Twitter. I'm at Space Brendan. This program is at AWTY or shoot me an email. It is arewethereyet@wmfe.org. All right, back to space. So I'll link to that story on the deep space power shortage on the show's website at wmfe.org/arewethereyet. But here's the gist of it. Deep space rovers use this thing called a radioisotope thermoelectric generator. We're going to call it RTG for short. And this is how it works. When something radioactive decays, it gives off heat. In this case, it's a marshmallow-sized chunk of plutonium-238. And on these rovers is an RTG, and it's a device that's able to use that heat that's generated from the material decaying and turn it into electric power. Now, the great thing about RTGs is plutonium decays for like a really long time. We're talking decades. So it's constantly providing heat and thus providing power. But at the end of the Cold War, the U.S. scaled back its nuclear weapons production, and a byproduct of that was, well, that scaled back plutonium-238 production. That was a product of weapons manufacturing. So after that, there was a diminishing supply. And not until recently did the U.S. Department of Energy get the funding and the go-ahead from Congress to produce more plutonium for NASA to use. Now, they figured out a way to make it without using the big nuclear reactors they used for weapons manufacturing, but they're ramping up production, and it's going to be almost 1.5 kilograms a year for folks like my guest to use. Now, Jim Green is the director of NASA's Planetary Sciences Division. His job is to oversee all these deep space probes and rovers, and he gave me a call to talk about how important RTGs are to deep space exploration. So, Jim Green, can you kind of tell me about the role these RTGs play on current NASA spacecraft?
You bet. It's important to note that the radioisotope power capability that we have is not just for deep space. The ability to bring one's own power allows us to do a whole variety of things, such as grabbing a sample from Mercury. Now, Mercury is awful close to the sun. Why do I say we need radioisotope power? We wouldn't do it from the day side. We would do it from the night side because Mercury is so hot. How about crawling into a permanently shadowed crater on Mercury or even on the moon? Now, that's important for us because what's in these permanently shadowed craters we're now sure of is some really early primordial material, cometary material, from the collapsing cloud and from comet impacts, from the very beginning of our solar system. So the ability then to get into places where the sun doesn't shine or shine very low, another example of shine very low would be the polar caps of Mars. Mars has got some fabulous polar caps. We go to our polar caps, core ice, read that ice, and it tells us the history of climate here on Earth. Well, we want to do that on Mars. We don't have the information about the history of Mars. We only have models. And so the ability to go to something like a polar cap, create an ice core, and then look in the past history of Mars is just dynamite. It tells us how that planet's evolved over, several billion years perhaps. So the key element that I'm trying to mention is, yes, we need radioisotope power to go to Pluto or Uranus or Neptune, but we also need it in other places too. Places that you wouldn't originally think we'd need it.
Jim Green, that's interesting. So you're saying that using these RTGs, we're able to look on, the dark side of things, looking at the shadow of things that we've never been able to see before.
Right. So if you were to go into a cave looking for life here on Earth, and you're looking for microbial material, you would take a flashlight, right?
Of course.
Yeah, sure. So on Mars, we found caves on Mars. We have found collapsed lava tubes, which may actually harbor life. We don't know that for a fact, of course. But our ability to crawl into a permanently dark area like a cave on Mars looking for life, or connect to an aquifer, which is under the ground, in some way, we'd bring our own power. And that's where radioisotope power is absolutely essential for us to bring.
Are those radioisotope RTGs being used on current Mars rovers? Let's say, does Curiosity have one of these systems on board?
Yes, there is. So Curiosity is sitting in a crater on Mars, and it has about 110 watts of continuous power generated from the RTG that's connected to the back end of it. Now, that allows us to charge up batteries, to run a whole variety of experiments, whether it's morning or evening or night, okay? Now, that's important because we have a lot of analytical instruments that can be doing their data analysis at a different time of the day. We're not constrained by only having the opportunity during the work day when light is plentiful to be able to work on Mars. So Curiosity has it. The next rover that we're building is called Mars 2020. We haven't given it a name like Curiosity yet, but that will happen. And that particular rover will also have radioisotope power. Now, Spirit and Opportunity, the first really sophisticated rovers that we sent to Mars about 15 years ago or so, those rovers used solar power. And, we had thought that they were going to last, we wanted to make them last 90 days, okay? And they've far exceeded that. And the reason why we thought they would only last 90 days is because Mars's atmosphere, like our own atmosphere, which has dust, but at Mars, with the thin atmosphere and the very low winds, it can actually, this dust can filter out, accumulate on solar panels, and then block the light of the sun and then cause the rover to freeze. And that's what's happened with Spirit. But Opportunity is still going great, and that's because we've had a variety of cleaning events from the atmosphere that we didn't expect. These are these dust devils that come around and clean off the solar panels, and voila, we got the power for the next day. But for Opportunity to really survive, there's a lot of work that goes into power management, a lot. So during the winter, it actually has to winter over on Mars. It really can't survive through the winter. It's not enough light. So what it does is it finds a location where there's a hill that's got a good 20 degrees tilt to it, and then runs up the hill such that it's pointing its solar panels directly to the sun. And then it will do a variety of science in and around the area that it's parked. So that goes on. But in reality, it's really hibernating over the winter mostly until the sun rises high enough that it then can take off and go about its normal daily business. So power management for these rovers can be really quite extensive.
So the ultimate goal is, put humans on the surface of Mars, but these rovers are kind of laying out the groundwork how important is this this RTG, this plutonium power supply? How important is it to our efforts of putting humans on the surface of Mars?
Okay. So it's critical. I don't know if you saw the movie The Martian.
Yes, I did.
So Mark Watney runs out and he digs up the radioisotope power system. And although in the book he actually does a lot with it, in the movie he uses it for heat. And it turns out not only does it provide adequate power, but it provides a whole heck of a lot of heat. And we actually have heat pipes that run off the radioisotope power systems on Curiosity and run through the rover itself, which heats up our experiments and keeps them pretty close to room temperature. That's how come the rover operates in an operating condition sitting on the surface of Mars that could literally be 120 or 130 degrees below zero. Okay? That's because the rover's toasty.
Now, would you ever recommend, let's say I get stranded on the surface of Mars, would you recommend if I dig up one of those RTGs to help keep myself warm?
Well, it is radioactive. There is a danger associated with it, but it's minor in comparison to the environment that you're in. So, I was a consultant on the film, and I told him, when he pulls it out of the ground, have him wrap it and stick it in his rover, and he'll have plenty of heat, and that will overcome his problem. And that's what they did, versus the book, which had a lot more intricate manipulation of the RTG. But in any event, it does produce a mild amount of radioactivity that humans, live and work around them to be able to construct and build them and then put them on the rovers at the Cape before we launch them. And so they have to be pseudo-radioactively safe. But they still generate radiation that can be harmful over long periods of time for long exposure.
But that's the least of my worries if I'm stranded on Mars.
That's the least of your worries if you're Mark Watney stranded on Mars. That's exactly right.
Now, with that said, is there any talk about using the heat generated from these RTGs or the decay of let's say plutonium to be used to heat something like a habitat on the surface of Mars or even the surface of the moon?
Well, that's going to happen naturally because you either throw away the heat because it's waste or you use it. So I can guarantee you they'll use it. Now, the kind of power that it generates and the kind of heat that it generates are great for robotic systems, but human systems are going to require a lot more work in that area. So when we go to Mars, we're probably going to be using a variety of resources. One resource to provide heat. So one resource might actually be methane. We know Mars emits methane. We don't know if that's generated biologically or abiotically, but we do understand that there are some methane vents on Mars where a significant amount of that methane can be emitted over long periods of time. If we're in the right area, man, that's like your gas stove. You can heat stuff. You can create an environment that's more livable by using the availability of a resource that's there.
So I want to kind of move away from Mars and kind of talk about RTGs and the sourcing of that plutonium. Now, when you didn't have a steady source of plutonium and you didn't know where that manufacturing was coming, did that kind of limit the scope as to what you could do exploration-wise throughout the solar system?
Right, that's a good question. That used to be the case. We used to be worried that we would be running out. And why is that? Because 1982, in the SALT II agreement, when the radioisotope material in terms of its generation was limited, they stopped making the material that produced the plutonium-238. So that means since 1982 we had a dwindling supply of plutonium-238. Well, over the last several years, we worked very hard with the Department of Energy and the administration and Congress to be able to get a law passed that allows us to pay for restarting the production of 238. And in fact, the Department of Energy now has began a process that actually irradiates neptunium in a reactor and generates the plutonium we need, and then goes through the extraction process to be able to get it. That process has never been used before. They've verified that it's doable, and that all their equations and all the nuclear physics that is involved in understanding how this stuff can be generated is validated. And now they're putting in place on a regular basis the ability to generate 1.5 kilograms a year. Now, we currently have a stockpile of plutonium, and the 1.5 kilograms a year is important for us to be able to add to our stockpile to be able to produce adequate fuel. So that means what you had heard, that we are running short of plutonium and we don't have enough plutonium, is really old news. That's no longer the case. We've worked with the Department of Energy. We have congressional funding, administration backing to be able to restart plutonium production, and we're well on the way of demonstrating it and putting it into operation.
So looking back and knowing that there could be a limited amount of this material, did that kind of limit the places that you could go in the solar system with these exploration probes? And does having that steady source now from the Department of Energy, does that change the amount of places that you are starting to look to explore?
Yeah, that's a really good question. So let me take the first part. When we had a limited resource, we did indeed think in a limited way on how to conserve it. And so consequently, we were quite concerned about how we would develop systems that could use it that would conserve that material. And then we invested in a variety of plans to look at that. However, now that we can make it, we can use our existing capabilities, and indeed, it opens up a whole new set of things that we can do, as I mentioned earlier, because we can replenish our supply. So I'm looking into a future for NASA for which planetary science is currently going to be a good steward of the program by having the opportunity to continue to make, through working with Department of Energy, which actually makes it and stores it for us, all the plutonium that we're going to need for our upcoming missions. So where we were conservative, we now can be much more visionary about how we can go and use the material to missions in those places we talked about earlier, in the outer parts of our solar system, or even on objects closer to the sun.
With that said, and having basically limitless opportunity when it comes to powering these probes, is there a particular mission, maybe past Mars 2020, that you're particularly excited about? And I know that might be a hard question to answer.
Yeah. So I'm head of planetary science, and I love all my children equally. So, but I love the opportunity that this material provides for us to go and visit some planets that we really don't know a lot about, and these would be the ice giants. I really enjoy the opportunity to be thinking about how we could even visit water worlds, ocean worlds like Titan, who has methane lakes on its surface. and Enceladus, where we could fly through the plumes, things that are gonna require radioisotope power to be able to get out to Saturn and those places. So there's a whole slew of stuff that we can do now, and really think about how we can use it as the program is evolving over the next 10 years or so.
Jim Green, before I let you go, is there anything else you'd like to talk about with our listeners?
What I say, is an important thing to remember is two things. One, radioisotope power is a mission-enabling capability that we use all over the solar system. And two, we now are in a position where we are good stewards of the program. We're working hand in hand with the Department of Energy, generating the plutonium that we need, and allows us to think about some really creative missions in the future.
That was Jim Green. He's the director of NASA's Planetary Sciences Division. Well, that about does it for this episode. Support for Are We There Yet comes from the listeners of WMFE. Follow the show online. We're at Twitter at AWTYMars, or reach out to me in the Twitterverse. I'm at Space Brendan. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. Find more space news online at WMFE.org/space. I'm Brendan Byrne. Thanks for listening.